All right, everyone. So there was just a little bit of a hiccup with the recording software. So I'm starting over, but instead of redrawing everything, I'm going to just jump right into the already drawn figure and work my way through the explanation. So we're picking up right where we left off with phase 2 of glycolysis. So in phase 2, we've set everything up through the investment of a pair of ATP. We've added 2 phosphates to glucose. We've rearranged it structurally into a fructose, and we've divided it into a pair of trioses, the glyceraldehyde 3-phosphate. So entering phase 2 of glycolysis, everything that I write here in phase 2 is times 2, because per unit glucose that went in initially. So I'm going to keep everything here drawn as 1, but you can think of it energetically as 2. So for every glucose in, there will be 2 glyceraldehyde 3-phosphates, 2 1,3-bisphosphoglycerates. In terms of outputs, we'll have a pair of NADH and 2 pairs of ATP. So on that note, what we start with is glyceraldehyde 3-phosphate. And glyceraldehyde 3-phosphate is going to get oxidized. The aldehyde on the 1 carbon here is going to undergo an oxidation event and go from the aldehyde to an acid. But that acid is going to be phosphorylated simultaneously. And to accomplish this, as inputs, we're going to need an inorganic phosphate and an equivalent of NAD+. So glyceraldehyde 3-phosphate will be acted on by the enzyme glyceraldehyde 3-phosphate dehydrogenase. It's going to take the NAD+ and the inorganic phosphate, and it's going to phosphorylate and oxidize to 1,3-bisphosphoglycerate, or BPG. This is going to put a second phosphate on the triose, and it's going to produce an equivalent of NADH. Now remember, NADH is also going to be important in subsequent chapters and pathways when NADH is going to be important for the production of more ATP. So as a reducing equivalent and energetic output, it's also significant in addition to the ATP, even though most of our discussion about inputs and outputs for this particular cycle seem to revolve around ATP. Now, in terms of delta G, is this a favorable reaction? Well, when it's all said and done and coupled, delta G under standard state conditions is slightly positive at 6.3 kilojoules per mole. So it's not favorable in the sense that the reaction does not favor products over reactants. However, it is lingering close to equilibrium. It's not a highly positive or highly unfavorable reaction. And what we'll see in subsequent reactions is that this less favorable reaction that's operating near equilibrium will be pulled through via Le Chatelier's principle by highly favorable reactions. So, moving along, we are now at 1,3-bisphosphoglycerate, or BPG, and 1,3-bisphosphoglycerate will be acted on by phosphoglycerate kinase, and this is going to be the metabolic break-even point in terms of ATP investment. So far, per glucose, we've invested 2 ATP to get to this stage, and at this point, per glucose, we will net 2 ATP back, 1 per glyceraldehyde 3-phosphate. So 1,3-bisphosphoglycerate plus ADP in the presence of phosphoglycerate kinase will yield 3-phosphoglycerate, or 3PG. And what you'll notice here is that we've dephosphorylated at the 1 carbon, leaving a carboxylate. So even though we've gone through a dephosphorylation, recapturing that phosphate in the form of ATP and energetically breaking even, we've also maintained the oxidation at that first carbon. Now, this process is quite favorable, with a delta G of negative 12.6 kilojoules per mole, and it's favorable enough to fundamentally drag the prior 3 reactions along. So even though we had a sequence of reactions that were operating at near equilibrium conditions slightly unfavorably, it just takes one good favorable reaction to pull everything through. Following the formation of 3-phosphoglycerate, 3-phosphoglycerate is going to be acted on by phosphoglycerate mutase, and it's going to form 2-phosphoglycerate. Now, let's lean on the chemical rationale for this particular step a little bit. Why are we moving the phosphate from the 3-carbon to the 2-carbon? Let me draw that in a little bit more clearly. Well, the reason for this is because the following reaction is going to involve a dehydration between the 2nd and 3rd carbon, the formation of a double bond. And to do that, we need to remove a hydrogen and a hydroxyl group. Well, with the presence of the phosphate on the 3-carbon, we can't really do that. So by moving the phosphate from the 3-carbon to the 2-carbon, we allow for the formation of the following phosphoenolpyruvate, which can then subsequently, in the formation of pyruvate, release a substantial amount of energy. So this is just priming the structures so that we can advantageously capture energy in a fashion with maximum efficiency. Now, once again, if we take a look, under biological conditions in erythrocytes, delta G is very close to equilibrium for this particular reaction. We're not seeing any net loss or gain of electrons, and we're also just, meaning there's no oxidations or reductions taking place, we're just rearranging bonds. So the total amount of energy between the two is really still similar. Now, the following reaction, the conversion of 2-phosphoglycerate to phosphoenolpyruvate, or PEP, takes place through enolase enzyme in the presence of potassium and magnesium. And in this particular step, you see that dehydration I was speaking about, where the hydroxyl group off the 3-carbon and the hydrogen off the 2-carbon get pulled off as an equivalent of water, forming a new double bond between the 2nd and 3rd carbon and leaving the phosphate on the 2nd carbon. And this is phosphoenolpyruvate, and this particular reaction is also operating right at equilibrium with a slightly positive delta G under standard conditions of 1.8 kilojoules per mole. So in terms of why we're doing this, other than setting up a double bond, what is the purpose of the double bond, and why are we really taking 2 compounds that have nearly identical net chemical energies and rearranging them? Well, we can get some clarity around this by realizing that the 2-phosphoglycerate and phosphoenolpyruvate contain about the same amount of potential metabolic energy if you're just looking at decomposition of phosphate, CO2, and water. But what the enolase reaction does is it rearranges the substrate into a form with more of its where more of the potential energy can be released upon hydrolysis by forming this enolate, which will then rearrange to the keto form in the following reaction, and we'll get a substantial amount of energy out through that mechanism. So let's take a look at that reaction. So phosphoenolpyruvate, through the actions of the enzyme pyruvate kinase, yields pyruvate, which looks like this. And this particular reaction is coupled to the formation of another equivalent of ATP. So this is the point in terms of ATP where we previously broke even. We're now capitalizing metabolically on this pathway, and we're gaining net ATP back. So per glucose, we're going to gain 2 total ATP per cycle of glycolysis. And this is the final step in glycolysis. Now, how energetically favorable is this? Well, delta G for this particular step is a very impressive negative 31.7 kilojoules per mole. Therefore, equilibrium for this particular reaction lies very far to the right, very far towards products, and will effectively pull the preceding reactions through the Le Chatelier's principle. Now, why is this particular reaction so favorable? The high free energy change for the conversion of phosphoenol pyruvate to pyruvate is largely due to the highly favorable and spontaneous conversion of the enol tautomer of the pyruvate to the more stable keto form. And this is really the crux of why we went through all of the work chemically to move the phosphate from the third carbon to the second carbon and then undergo a dehydration reaction, because there was so much energy regained in the conversion of the phosphoenol pyruvate to the pyruvate. Additionally, anchoring glycolysis with such a highly favorable final step makes the overall reaction substantially more efficient. So the large negative delta G for this reaction makes pyruvate kinase a fantastic target for regulation of glycolysis. Along the same lines that we've seen, whenever we have major energetic investments or energetic outcomes in terms of ATP in or ATP out, these sites or steps are the ones that get the most attention in terms of biological regulation. So for each glucose molecule in glycolysis pathway, 2 ATPs are made at the pyruvate kinase stage. Because the pathway broke even in terms of ATP at phosphoglycerate kinase reaction, the 2 ATPs produced by pyruvate kinase represent a payoff. And pyruvate kinase possesses allosteric sites for numerous allosteric effectors. It's activated by AMP and fructose 1,6-bisphosphate and inhibited by ATP, acetyl-CoA, and alanine. So let's write those down. Take the time to write those down. Oh, and now I'm dragging things around. So allosteric effectors. Let's see if I can get rid of that. So there's 2 categories of allosteric effectors. There's the activators. Sorry. See if I can do this without dragging activators and inhibitors. And the activators include AMP and fructose 1,6-bisphosphate. Both of these should make sense in terms of rationale, because if we're turning glycolysis up by driving it to completion through increased activity of pyruvate kinase, that should indicate an overall need for more energy. So low energy status indicators like AMP make sense. Now, in terms of inhibitors, Inhibitors include ATP, acetyl-CoA, and alanine. These likewise make sense because ATP is our universal indicator of energy status. Acetyl-CoA, we'll find, is an input into the TCA cycle as well as lipid synthesis. And alanine is an interesting one because alanine is an amino acid counterpart to the alpha keto acid pyruvate. And it's also going to link glycolysis to aspects of liver function and amino acid metabolism. So not only are we seeing effectors which generally reflect energy status, but we're also seeing effectors which are tying critical aspects of primary metabolism to one another, so we get some crosstalk between their metabolites and with whole organism integration, which is really essential to efficient function. Now, in addition to just being allosterically regulated, pyruvate kinase is also regulated by covalent modification. Which we discussed in first semester biochemistry as a general concept. Now, in the liver, hormones such as glucagon activate cyclic AMP-dependent protein kinase, which transfers a phosphoryl group from ATP to the enzyme, phosphorylating the enzyme. And this phosphorylated form of pyruvate kinase is more strongly inhibited by ATP and alanine and has a higher Michaelis-Menten constant for phosphoenol pyruvate. So in the presence of physiological levels of phosphoenol pyruvate, the enzyme is functionally inactive. So to quickly review that, if you have a phosphorylation enzyme, that phosphorylated enzyme is going to be more strongly inhibited by ATP. And acetyl-CoA, or alanine, and alanine. And it's going to have a higher Km for PEP, which is the substrate. Meaning that under normal physiological levels, it's not going to be active because it's not going to be binding the substrate. And under these particular conditions where we have phosphorylated pyruvate kinase at the liver, which is increasing the Michaelis-Menten constant for PEP, we're going to have an increased pool of PEP, and that PEP is going to become a substrate for glucose synthesis, entering gluconeogenesis. Or storage of carbohydrates in the liver. So we get some dual modes of regulation, cooperative regulation between covalent modification and allosteric regulation in the final step of glycolysis. And finally, to wrap up this chapter, now that we've completed glycolysis, we should talk a little bit about metabolic fates of NADH and pyruvate produced by glycolysis. So I'm going to ignore some of the classic anaerobic metabolisms of pyruvate, which include ethanol, because that's microbial, and the focus of this course is mammalian scale metabolism as it applies to more sophisticated models. Now, where that's really particularly interesting is the accumulation of lactate under anaerobic conditions. So let's talk about lactate, or lactic acid. So in animal tissues experiencing anaerobic conditions, pyruvate is reduced to lactate. And pyruvate reduction occurs in tissues that normally experience minimal access to blood flow. When skeletal muscles are exercising really strenuously, getting all pumped, the available tissue oxygen is going to be consumed rapidly, and the pyruvate generated by glycolysis can no longer be oxidized in the TCA cycle because we just don't have enough oxygen available to meet the rate of energy demand. So instead, excess pyruvate is reduced to lactate by lactate dehydrogenase. And the rate of anaerobic glycolysis in skeletal muscles can increase up to about 2,000-fold, almost instantaneously. For example, to support the intense demands of a sprinting animal, we need a lot of energy really fast. So large amounts of ATP are generated rapidly at the expense of accumulating lactate. In anaerobic muscle tissue, lactate represents the end of glycolysis. Anyone who exercises to the point of depleting available muscle oxygen stores knows the sensation of cramping and fatigue and burning associated with the buildup of lactic acid in muscles. So now what's interesting is most of the lactate needs to be carried out of the muscles by blood and transported back to the liver, where it can be resynthesized into glucose in gluconeogenesis, which we're going to cover in chapter 22. Moreover, because glycolysis generates only a fraction of the total energy available from the breakdown of glucose, the onset of anaerobic condition in skeletal muscles also means a reduction in the energy available from the breakdown of glucose. So it's a trade-off. It's a lot of energy really fast, but at the expense of the efficient abstraction of energy from the glucose. So it's a necessity, but it's an expensive necessity. So let's take a look in a little bit of detail what this pathway looks like, and that's going to be it for chapter 18. So what we're going to see is under anaerobic conditions, starting with glyceraldehyde 3-phosphate, we're going to, through the glyceraldehyde 3-phosphate dehydrogenase enzyme, we'll be able to produce 1,3-bisphosphoglycerate, and this involves the investment of an NAD in an NADH plus proton out. Now, let me make a little bit of room here, a few steps, we end up with pyruvate. Oh, sorry, this is 1,3-BPG. And under anaerobic conditions, instead of being entering the TCA cycle and undergoing oxidative metabolism, pyruvate gets acted on by lactate dehydrogenase, producing lactate. Which is simply the reduction of the 2-carbon from the ketone to the alcohol. And in doing so, we consume an NADH, which is our reducing equivalent, and regenerate NAD+. And that is going to be it for chapter 18. So the next chapter is going to be, I believe, the tricarboxylic acid cycle, or TCA cycle. And we're going to follow the oxidative metabolism of pyruvate to acetyl-CoA to citrate, isocitrate, alpha-ketoglutarate, succinyl-CoA, succinate, fumarate, malate, oxalo acetate, and all the details that connect those steps. So I'll be talking to you about that next week.